Welcome to the fourth installment of 6034 Fall 2020 Recitations. Today we're going to be talking about rule-based systems. And in it we're going to see at first I'm going to lay the groundwork with a few definitions. Then we're going to go over the basics of forward and backward chaining. And we're going to work through an example of both. And then there's an extra concept that I'll want to teach at the very end regarding knots and how these rule-based systems are in fact brittle pattern matchers, and how they may give the impression that they're performing common sense reasoning, but in reality, it's just pattern matching. Okay. So here we have the the agenda as always, and first we're going to move on to the definitions that we're going to need for rule-based systems. Okay, so first is the anatomy of a rule. A rule consists of an if statement, the condition that has to be met, and whatever's inside the if statement we refer to as the antecedent. Then is the result of meeting the conditions contained in a then, and because it's a result of meeting the conditions, we refer to this as the consequent. And then rules also have a particular, I'm going to start and make an asterisk here, delete clause, which, as the name implies, mutates the data by removing certain assertions that you may have, and we'll define assertions briefly. It removes assertions, or maybe removes something else. Maybe it removes a rule. But in reality, because they mutate the data as a program is running on it, they introduce a lot of complexity in edge cases that is not covered within 6034. So for the moment, we're going to say that delete statements are optional, and we won't be seeing them in 6034. And then onto the assertions, which is what powers our rule-based systems, is basically statements that we hold to be true. Scratch that off with basically, they are the statements that we hold to be true. And you'll see them they're numbered usually within the examples that we discuss here in 6034, and the one that we're going to discuss in this recitation: A0, A1, A2, so on and so forth. And then rules can be P0, P1, P2, so on and so forth. And what would happen is there's an interaction between the consequence of the rules and the assertions that we have, and I'll show you briefly how that works in a brief rundown of forward and backward chaining. And obviously after this small introduction, I'm going to go more into detail about forward chaining first. So the first thing in forward chaining is that we start with the assertions. And then we apply the rules until we're finished. And I'll highlight this briefly. Finished is, we'll discuss what finished means in this case, but there's a very clear point at which our program execution is done. Then for backward chaining, we start with a hypothesis instead of the assertions. And then we build a goal tree. Again, this is only a brief overview. I'll discuss both of these in more detail, starting with forward chaining. And for forward chaining, it's straightforward enough that I've put together some rudimentary pseudocode of how the process would look on pen and paper. It's by no means meant to be an implementation of a rule-based system. It's meant to, in a nitty-gritty way to some extent, define how, given a problem of forward chaining on pen and paper, you would go through the rules, the assertions, and fulfill the goal. So first I'm going to create an empty list that I'm going to call matches. And now I want to start a loop. And what I want to do is I want to loop through all the rules that I have. I'm going to make a variable called allRules. And you may assume allRules is basically, if in tradition with the example that I used at the beginning when I was defining the anatomy of a rule, it's a list of P0, P1, P2, so on and so forth. Actually, if we want to make this more akin to Python, there we go. Now, once I'm looping through each rule, let's say I have P0, I want to check all the assertions that could potentially match P0 for each assertion in all assertions. And again, I'm going to write the comments in green because I think of Python comments being green. I forgot it with the above comment. So this is going to be a list of A0, A1, so on and so forth. If there's a match, assume that I have a function that is able to tell whether an assertion and a rule match between the rule's antecedent, the part in the if, and the assertion, then I want to update the rule. And that's what this hypothetical function is going to do here. Let me make this clear. There we go. And I want to update the rule so that the consequent of that rule is a result of the assertion that met the condition in the first place, that met the antecedent. And again, you'll see what this means in the example. Then finally, once I have this rule match, I want to add it to my list of matches. Okay, so I have a list of matches now after I've gone through all the rules and I've gone through all the assertions. What do I do now? Well, now I need to evaluate every single rule match. And now that I'm evaluating those, I'm going to start writing rule match in red. Rule match in red being the object of interest. Now I want to check, is the consequent of the rule, after updating it with the assertion that met the condition in the first place, is that consequent something that I didn't know before? What that means is, and here in code, I'll show you, is the assertion that basically the consequent turns into a new assertion once I update it with the previous assertion. Is this new assertion in my list of previous assertions. So here I'm testing, did I already know what this rule is telling me? And if I didn't, then that rule is going to fire. And what it means to fire is that the new assertion is added to my current list of assertions, so I now have more ground truth knowledge, more statements that I hold to be true, and we restart the process. So now that I have one more assertion or two more assertions, depending on how the consequent of the rule is structured, then I need to recheck all the rules and all the assertions and see how the panorama has changed. In order to put this into practice, we're going to follow the following example. This is an example of a rule-based system based on the matrix, and we're going to determine, or we want to find out whether Neo is the one. And we're going to do so by taking these first four assertions, A0 through A3, and P0 through P5, and we're going to do forward chaining using them. Allow me to change the view so that we can both see the prompt, the rules and the assertions, and the table of what's going on at the same time. I highly recommend that once you're going to solve a forward chaining problem, you make it a table, because it'll keep you very organized, and it's a very structural way of seeing the iterations go by. So what's going to, following in the spirit of the pseudocode, I start with P0. So I take a look at P0 over here, and I see X visits P oracle, or that would be the consequent. My apologies. I need to read the antecedent, either X is a noob or X is disenchanted. And I go through my assertions one by one. I see Neo is a noob, that's a match, which means I update P0, and which P0, then the assertion in P0 becomes Neo visits the oracle. Trinity is disenchanted, that's also a match. Trinity loves Neo and proclaims love for Neo, those aren't matches. And I perform the same operation for each of the rules. And I encourage you to inspect the rules one by one, but I'm just going to jump ahead and say that P4 is also a match. And for iteration 1, it's only P0 and P4. P4 is a match because in this AND, we have in the assertions that Trinity is disenchanted and Trinity loves Neo. So once we update P4 with these assertions, we say the assertion provided by P4 is Trinity proclaims love for Neo, where the match happened because X was equal to Trinity and Y was equal to Neo. But we're only interested in one, at least for the moment, only one. So I'm going to write these down, P0 and P4 match. And the important thing to note is only one rule may fire per iteration. And once the rule is fired, we add the assertion, and then we restart. So let's continue with the example first. So the first thing to fire, the first rule to fire, is P0 with X equal to Neo. And the reason we know that is because P0 is the first rule, and A0, the matching assertion, is the first assertion. So that's the first thing to match, which means it's the first item in the list of matches in the pseudocode, and that's the first one to be checked. And when we update P0, Neo visits the oracle, I check A0 through A3. None of them say Neo visits the oracle, so P0 can fire with X equal to Neo. And I get the following new assertion. Neo visits the oracle. And because we had a rule fire, we break, we stop the execution, and we restart. So iteration 2. Now ask yourself, P0 and P4 matched. Will they match again this next iteration? The answer, you shouldn't even need to look at the rules. The answer is yes. And the reason it's yes is because we don't have any delete statements in our set of rules. So the assertions that we have is never going to change in the negative direction. We're never going to lose an assertion. We're only going to get more assertions, which means any rules that match previously or in the previous step are guaranteed to match in the next step in this setup that we have if there are no delete statements. So we know that P0 matches and we know that P4 matches. Is there anything new that's matching? And let's take a look at P1, for example. If X visits the oracle, then X picks the 1. A4 is that Neo visits the oracle, which means P1 is a match. Anything else? And X is a noob, X visits the oracle. So P2 earlier didn't match because it's an AND. Both arguments or all the arguments inside an AND must match in order for an AND to yield true. So we had X is a noob in A0, and Neo is a noob, but we didn't have X visits the oracle, which we do now. So P2 is a new match. And now, would P1 be the one to fire? That is I'll give it away, obviously. It's a no. And actually, P0 fires again. But this time, X equal to Trinity. I've abbreviated Trinity Trin for space reasons. And the reason it does is we would check rule 0, assertion 0, there's a match. Rule 0, assertion 1, that's another match. And when we update with assertion 1, there's in the list of matches, there's rule 0 updated with assertion 0, rule 0 updated with assertion 1. And when we go to check that list of matches, obviously we just added rule 0 assertion 0, but we hadn't added rule 0 assertion 1. So and it's clear to see the consequent there would be Trinity visits the oracle, and that's not in the list of assertions right now. So we get a new assertion from P0. Okay? Number 3. We already know that P0, 1, 2, and 4 are going to match because there are no delete statements. So let's just evaluate whether P3 and P5 match at this point. P3 says there's an OR first. Is disenchanted is a noob. We know those match because we have that Neo is a noob and Trinity is disenchanted. But then the AND says the oracle says X is not the 1. We don't have any assertion that looks like that, so that doesn't match. And then there's an and it starts with for P5. The oracle says X is not the 1. We just confirmed there's no assertion that says that. So P5 and P3 are still not matching. So I'll just rewrite P0, P1, P2, and P4. And now I don't have to think much in order to see that P0 is not going to match, because currently in my list of assertions, I only have X equal to Neo and X equal to Trinity, and P0 has already fired for both X equal to Trinity and X equal to Neo, which means presently there's not any assertion that would make P0 fire again. If later on I get a rule that says, or an assertion that says Hector is a noob, then P0 would fire again. But for now I don't need to check it. And P1 is going to be the one that fires for X equal to Neo. And let's see what it says. Then X being Neo picks the 1. That's not an assertion that we already have. So we can add this as A6. Neo picks the 1. Okay, so as I said before, we still don't have any assertion that says the oracle says x is not the 1, and this is fundamental for P3 and P5 to match. So we stick with P0 through P0, P1, 2, and 4. Okay? And now the one to fire now is, let's see, P1 matched with visits the oracle, and we have both Neo visits the oracle, Trinity visits the oracle, so P1 can fire for x equals Neo. X equals Trinity. Again, abbreviated for lack of space. So we get an assertion similar to the one above. Trinity picks the 1. Now iteration number 5, same as before. There's nothing about visiting the oracle. There's nothing about the oracle saying x is not the 1. So same set of rules as the one to match. P1, the same as P0 earlier. It fired for both x equals Trinity and x equals Neo. Therefore, I don't need to bother checking, and I'm just going to check P2. P2 for x is a new, I know it matches for x equals Trinity, and for, not Trinity, for x equals Neo. Because A0, Neo is a noob, and which one is it? A4, Neo visits the oracle. So I just set A0 and A2, x equals Neo, and then the resulting assertion would be the oracle says Neo is not the 1. Neo is disenchanted. Those are 2 assertions. And they're both new, so P2 fires. I'm going to write them both. Space is a little scarce here, unfortunately. Last assertion, Neo is disenchanted. Wasn't 8, assertion 8, the assertion that we were missing for P3 to match? And also for P5, let's see. If and already the second half of the and is met, the oracle says x being Neo is not the 1, and in fact A9 meets Neo is disenchanted, and A0 meets Neo is a noob. So P3 matches, and P5, oracle says Neo is not the 1, Trinity proclaims love for Neo, and Trinity picks the 1, A7. So they both match now. I'm going to abbreviate, iteration 6, I'm going to abbreviate P0 through P5 because they all match now. And the next one to fire is P3 because P2 didn't. If I set x equal to Trinity, Trinity is a noob, is not in the list of assertions, and so P2 would not fire, or it would not match, and therefore would not fire for x equal to Trinity, which means the next one down the list is P3. P3, and as we just verified, it does match, yes. Neo practices Kung Fu. That's not an assertion that we have yet, which means it can fire for x equals Neo. So A10, Neo practices Kung Fu. Okay, iteration 7. P0 through P5, they all match. Don't need to check again. And now which one matches? We know P3 doesn't match for, which one fires? We know P3 doesn't match for Trinity, x equal to Trinity. P4 matches for x equals Neo and y equals Trinity. Pardon me, for x equals Trinity, y equals Neo. But it wouldn't fire because we already have the assertion in A3 as what would come out of P4. Trinity proclaims love for Neo. It's already there, so P4 doesn't fire, and that just leaves P5. We know it matches, and it would be for x equals to Neo, and it would say Neo is the 1. That's a new assertion. A11, Neo is the 1. And awesome. So we found out what we wanted to in the beginning. The prompt being, is Neo the 1 at the very beginning. Now, one question. Does the program terminate execution at this point? And the fact of the matter is, I leave that as an exercise for you. The program, or the toy programs that we're running here in 6034, they only terminate once no rules fire. So I leave it as an exercise for you afterward to continue this iteration and new assertion, match, fire until no rules fire, to see how far it will get you, and it'll be good practice in terms of looking at the assertions, looking at the rules, matching which assertions are new, which ones aren't, and what matches, and what fires. It's an important point. But yes, do continue this exercise until no rules fire, and even if nothing fires at iteration 8, it'll be good practice just to see how you would, visually verify everything and determine, okay, nothing fired, the program execution is done. And for now, that's all for forward chaining. And let's move on to backward chaining. I'm going to change the view. There we go. Until we need to see the PDF again. So backward chaining is quite the opposite of what we were doing, because we're now starting with some assertions are things we know to be true. So it's not going to be an assertion, it's going to be a hypothesis. We want to confirm or validate whether this is true or not according to what we know about the assertions and the rules. Excuse me. And there are some subtleties in how we manage backward chaining, because we are progressively building a tree and we want to verify the branches of the tree. I'm not going to make it pseudocode because it's a little bit trickier, and it would take away from understanding the basic concept of backward chaining, and instead of complementing it. So I'm gonna write it explicitly in plain English as a set of steps. So first, given a hypothesis, obviously, we need to check whether the hypothesis we were giving is in our list of assertions. Okay, and if in fact it is in our list of assertions, we're done. Excuse me 1 second. Okay. The reasoning behind that is if we're given a hypothesis, we want to verify it. If a hypothesis is already in the list of things that we know to be true, then there's nothing to verify. We just go to the assertion and say, oh, this hypothesis is true, we're done. But if it isn't in the list of hypothesis or hypothesis, or if the hypothesis isn't in the list of assertions, then we need to find all the rules with consequence that match the hypothesis. And you see how this backward chaining notion starts to come to fruition, because we're now, instead of matching antecedents and using the consequence as new assertions, we're using the consequence themselves to go back to the rules. Before I get ahead of myself, I'm going to write it out explicitly. Using the antecedents, we build the tree of bound antecedents. Pay attention to this bound term. And by bound, I mean where the variables inside the consequence are bound to those that match the hypothesis, and then we keep that binding for the antecedents. You'll see this more clearly in the tree as we're building it. And finally, 4, we do depth first search. With backtracking if we get stuck. Yeah, that's the process. Now the example problem is going to be, we have the hypothesis, Neo is the one, and we want to verify, is this true, using backward chaining. So notice earlier it was, we wanted to find, it's a different approach, and it has its advantages and disadvantages according to forward chaining, but we should be able to validate Neo is the one, and we know we should, because forward chaining gave us that result. But we're, again, assuming we didn't do forward chaining, we're just doing backward chaining with the assertions that we had earlier. Here are the assertions and the rules again. Allow me to bring up my notes. Okay. I'm going to keep a running list of hypotheses that I've checked against the list of rules and assertions on the right-hand side of the board. And first I'm going to check Neo is the one. The way I do this is I go through the rules consequence. Well, first I check the assertions. A0 through A4 don't have anything useful for me. Right? Yes. And then I check all the consequence. And the only consequent that would be useful to me is x is the 1, with x being Neo. And that's where the bound antecedents comes into play, because now I have to start building my tree with the bound antecedents being wherever x occurred, then I would have Neo, because that's the x that matched the consequent of the rule. So I'm going to write out here that P5 was the one that gave me the match. And I'm going to try to make space for myself. The oracle says, because I'm reading directly from the antecedents of P5. It's bound, so instead of writing x, I write Neo. I write Y proclaims love for Neo because there's nothing obligating me to bind Y. in the consequent I bound x, y wasn't a factor, so I can leave y free floating for the moment. And then again I have y picks the 1. Okay, let me draw the branches here. I'm going to have to erase P5 there. These are all branches, and last thing to note is this is an AND node, which means all these branches need to, all the antecedents need to be met in order for P5 to be validated as true, or the consequence of P5 to be true. So the way we represent an AND node is by drawing this arc between all its branches, and that just tells the person seeing it that all these branches must be true. And because it's depth first search, we start with the leftmost child. I'm going to write it out explicitly here. Oracle says Neo is not the one. Okay. And I need to take a look at my rules again, the consequence particularly. And I see that the oracle says Neo is not the one is produced by P2. And I'm not particularly interested in the other consequent because it would be added as a secondary assertion. What I'm interested in is P2 would say that the oracle says that Neo is not the one. So I need to keep exploring the antecedents of P2. They're an AND. So I draw the arc. And I start Neo is a noob. And then Neo visits the oracle. I check number 3, Neo is a noob. And by simply looking at the assertions, A0 says Neo is a noob, so I don't need to verify this one any further. Verified. So the next one, Neo visits the oracle. I branch out according to P0. Neo is a noob. Neo is disenchanted. And notice I didn't draw the arc between the branches because P0 now is the first rule that we're seeing that has a OR node instead of an AND node. So any branch here that is validated to be true will make the whole node true. And it just so happens that we just verified Neo is a noob. It's in our list of assertions. So we know this to be true. And now that this is true, the whole node is true, which means this doesn't even need to be explored nor evaluated. So this is an example of a short circuit evaluation. Because we don't bother checking the rightmost branch of the node. So let me update my little book to the side, or my bookkeeping, number 5, and I'm going to write it out explicitly. And say this is a continuation of number 3. Okay, and now we take a look. This has been fulfilled, this as well, which means Number 2 is done. Now we need to verify y proclaims love for Neo. And now we have a small problem. The problem that we have is what is y? And we need some way of checking. So what we do now is we assign y to something, and then we verify, does the truth value work in this case? So what I'm going to do is for number 6, instead of writing the bound antecedent, because it wasn't obligated in the case of y, the antecedent wasn't bound or wasn't obligated to be bound to anything in particular, I'm going to write the binding myself as a step in this queue, because if it happens that it's wrong and we need to backtrack, what would happen is bind y to something else. So initially this is going to be my binding. Okay? And because I've bound this, let me write 6. Because I've bound this, I now check in my list of assertions this new binding. And I see assertion number 3, Trinity proclaims love for Neo, right? I'm looking at this one, which means for the moment, this is correct. And now, because I've made the binding, I'm going to, instead of writing y picks the 1, which is the next one on the list, I'm going to write the rule with that antecedent also bound. And this is more or less in order to illustrate this, let's say I am not able to confirm Trinity picks the 1. This is just an example. Then what would happen, the backtracking would look like this. I'm going to write it in blue, because it's just a hypothetical example. So 8 would look like this. Y is equal to Hector, and let's assume that I validated, let's say that assertion 4 says Hector, what is it again? Hector proclaims love for Neo. Then number 9 would be Hector picks the 1. That's a hypothetical example. See, where we make a binding and then we work with that bound antecedent down the tree until we have to backtrack, and in which case we undo. Okay, so back to where we were. Trinity picks the 1. We look for a consequent that would lead us to this, and that's P1. P1, its antecedent says Trinity visits the oracle. Number 8 would be this one. Now let's take a look. Trinity visits the oracle. That would be P0. I get 2 branches. It's an OR node. Trinity is an OOP. And Trinity is disenchanted. Now, this is this is going to be an example of why I didn't write the pseudocode. Let's say it's number 9's turn. Trinity is a noob. I quickly look at my assertions. Neo is a noob, Trinity is disenchanted, Trinity loves Neo, Trinity proclaims love for Neo. So I know that number 9 cannot be easily validated by via the assertions. I have to go into the rules and make more branches. But before going into the rules and making more branches, I decide to check the rightmost branch, and I see Trinity is disenchanted. Oh wait, Trinity is disenchanted, that's assertion 1. And to our benefit, this is an OR node, which means with the rightmost branch being true, we don't need to expand any tree for Trinity is a noob, which means we're going to short circuit this and just validate. Let me just write it here, short circuit, and just go directly to number 10 because Trinity is disenchanted is already in our list of assertions. This is correct, therefore number 8 is correct, this is correct, and all 3 branches of Neo is the 1 have been validated according to our rules and assertions, which means we have confirmed the hypothesis Neo is the 1. And this particular case is why, as I said before, I didn't write the pseudocode. And if for those of you who are more curious about how you would implement that, one conceivable way of implementing it is for each child, you check, is this child in the list of assertions? No, then I check the next child. And you can have this run every time it's an OR node, for example, because you could just basically fast track. Is this child in the list of assertions? No. Check the next child. Is it in the list of assertions? No. Then the third one, oh, it is in the list of assertions, then there's no need to expand any child. We can break out of here and go back up. So that's just a rough hand-wavy explanation of how it would look in terms of implementation, but this is how we complete this type of example in 6034. We're comfortable short-circuiting the left child in favor of the right one if the right child would speed up the evaluation. Okay. And that's the last thing that I'll cover regarding backward chaining. Now, finally, I want to switch back to the webcam view and the webcam and the iPad, sorry. And I want to go through an example of not. And this is where I want to highlight that these rule-based systems are not as smart as they seem in terms of execution. And so I've made one rule here. Both these conditions need to be met. That X has chocolate and the opposite, the negation of the truth value yielded from this rule. X does not like chocolate. And then X is happy. So intuitively, what does it mean? If X has chocolate and that same person does not like chocolate, in other words, the person likes chocolate, then that person is happy. Makes sense, right? So we have the following. John has chocolate. John despises chocolate. So intuitively, again, if John has chocolate, he wouldn't be happy about it because he despises it. Apparently it's, it's seething hatred to the point that he would be unhappy if he were near chocolate. So having it is a death sentence. Now let's look at what would happen if I were to do some forward chaining on this. Iteration 1, whoops, I forgot to change ink. Iteration 1. Now comes the big question. Does P0 match? And the big lesson of today is that it does match. And here's what happens. This is an AND. X has chocolate. John has chocolate. A0, which means this yields true. Not, however, means negation of whatever's inside here. And what this rule is going to look for is there an assertion that says, for example, John does not like chocolate? Do we have an assertion that says John does not like chocolate? No. So this rule, even though technically it means either the same thing or something very similar, it does not match this rule. And what happens when it doesn't match? Well, this antecedent yields false because nothing matched. And this not makes it true. So both of these now are true in the end, and the rule matches. And the rule fires. And I'll just add a big set of question marks here, because this is precisely what I wanted to show you today with this last concept, is that rule-based systems are very, very brittle. Because we got this because there's no exact match for this not rule. And what happens is the not is used basically to, in this case, no assertion matches this rule. Yes, that is correct. And that's what we're returning. No assertion matches this rule. Or this condition, this antecedent. And that's a little bit of how not works. It's basically nothing matches this. True. It's true, or if something matches this, then false. And it's a little purview of how brittle these systems are. So that's more or less the basics of how we cover 6034 in 6034 rule-based systems. You've seen the anatomy of a rule, including delete, even though we don't use them here in 6034. You've seen an example of how to work through forward chaining, how to work through backward chaining, and then a motivating example into being wary of the brittleness of rule-based systems, which are essentially pattern matchers. And I encourage you to try these out on your own time, and to try other example problems in the quiz archive or other example problems that you may find along the way. Now, that's all I have for today, so thank you for joining me, and I'll see you next time.